A Carnegie Institution for Science audio press release for September 24, 2014. Most stars are born in clusters, some leave home. New modeling studies from Carnegie's Alan Boss demonstrate that most of the stars we see were formed when unstable clusters of newly formed protostars broke up. These protostars are born out of rotating clouds of dust and gas, which act as nurseries for star formation. Rare clusters of multiple protostars remain stable and mature into multi-star systems. The unstable ones will eject stars until they achieve stability and end up as single or binary stars. The work is published in the Astrophysical Journal. About two-thirds of all stars within 81 light-years, or 25 parsecs of Earth, are binary or part of multi-star systems. Younger star and protostar populations have a higher frequency of multi-star systems than older ones, an observation that ties in with Boss's findings that many single-star systems start out as binary or multi-star systems from which stars are ejected to achieve stability. Protostar clusters are formed when the core of a molecular cloud collapses due to its own gravity and breaks up into pieces, a process called fragmentation. The physical forces involved in the collapse are subjects of great interest to scientists because they can teach us about the life cycles of stars and how our own sun may have been born. One force that affects collapse is a magnetic field that threads the clouds, potentially stifling the fragmentation process. Boss's work shows that when a cloud collapses, the fragmentation process depends on the initial strength of the magnetic field, which acts against the gravity that causes the collapse. Above a certain magnetic field strength, single protostars are formed, while below it, the cloud fragments into multiple protostars. This second scenario is evidently commonplace, given the large number of binary and multi-star systems, although single stars can form by this mechanism as well through ejection from a cluster. As Boss says, when we look up at the night sky, the human eye is unable to see that binary stars are the rule, rather than the exception. These new calculations help to explain why binaries are so abundant. These images show the distribution of density in the central plane of a three-dimensional model of a molecular cloud core from which stars are born. The model computes the cloud's evolution over the freefall timescale, which is how long it would take an object to collapse under its own gravity without any opposing forces interfering. The freefall time is a common metric for measuring the timescale of astrophysical processes. In image A, the freefall time is 0.0, meaning this is the initial configuration of the cloud, and moving on the model shows the cloud core in various stages of collapse. In B, a freefall time of 1.40, or 66,080 years. C shows a freefall time of 1.51, or 71,272 years, and in D, a freefall time of 1.68, or 79,296 years. Collapse takes somewhat longer than a freefall time in this model because of the presence of magnetic fields, which slow the collapse process, but are not strong enough to prevent the cloud from fragmenting into a multiple protostar system, as in D. For context, the region shown in A and B is about 0.21 light-years, or 2.0 times 10 to the 17th centimeters across, while the region shown in C and D is about 0.02 light-years, or 2.0 times 10 to the 16th centimeters across. The images are provided courtesy of Alan Boss. With the independence for nimble pursuit, Carnegie scientists tackle some of the most profound challenges in modern science, fundamentally changing what's possible for us, our planet, and our universe.